and then I'll hand it over to Rodvik so that we continue with the second day, which is training the data that you've generated. So um, I'll talk a bit about the company mission and some of the ideas behind the the the, the product that we're developing. And at Digital Blue Phone, we're looking at how digital technology can help us accelerate the digital transition of the AC industry towards building a more sustainable future. So we believe that digital technology can help us address some of the main challenges that the industry is facing right now. And I think that for all of us right now, by now, this is self-evident, and we all know these figures. But the question is, um, what do they actually mean, and what are we going to do about it? So if we think about it, we've heard the projection by the UN that says that by the year 2050, 6.6 billion people will be living in cities. And if we put that in perspective, what that means is that currently right now we're around 4.4 billion people living in urban environments. So this 6.6 billion figure translates to a growth rate of around 6 million people per month. So if you really think about it, 6 million people per month is something like a city the size of Barcelona, a mid-sized city in Europe. That's the urban growth that will be happening from now on until 2050. So that means that from now until 2050, we should be building every month a city the size of Barcelona. And at the moment, if we continue operating and we continue working the way we are working right now, we won't be able to meet the urban demands that are expected to happen in 2050. So we really need to reconsider and rethink the way we work at multiple levels. In parallel to this, and at the same time, we know that our industry is responsible for close to 40% of the world CO2 emissions. So not only just about how we design, but also in terms of what the relationship to fabrication techniques, to our relationship to materials and energy consumption, we need to rethink the way we operate at multiple levels. And last, we know that compared to other industries, our industry is lagging behind and adopting digital technologies. So if we look at any other industry in the past 20 years, there's been a huge increase in productivity in every industry that has adopted digital technologies for their work. If we look at the construction industry, in the past 20 years, the increase in productivity has been something like 1%, and this needs to change. And we believe that for this to change, we need to act now, and we need to completely reevaluate the way we work. So for this reason, we're looking at how to make these technologies available to everyone, not just a few experts in the field, but how we can integrate machine learning, AI, and data analysis and all these other technologies in the way people work in a user-friendly way in which more people can have access to these technologies, and that way we can actually have an impact in the way we're building the future cities. So at Digital Blue Phone, we're proponents of augmented intelligence as opposed to simply AI. So we're not just interested in automating tasks or using technology to replace certain tasks that humans do at the moment. We're interested in creating a dialogue between the human and the computer, a creative dialogue in which the human and the computer can co-create design. So one of the features that we've developed is the pen tool, which if you think about it, the way a human sketches, it's it cannot be translated into a machine learning algorithm or into a AI algorithm, because this responds to a different way of cognitive thinking, and it responds to the intuitive way that humans operate. So in a way, what we're trying to do here is translate this technology in a way that designers can integrate it to the way they have traditionally worked. And if we look at the construction process, the way it works right now is in a very linear fashion, and it is quite fragmented, and communication is poor between every stage of the process. So data is not flowing from one stage of the process to another, and communication is very hard between the different parts involved in the construction industry. So we're thinking about how we can create a platform that operates more as a operating system that will interconnect all the different parts and all the different people, and will facilitate communication, and will make data flow seamlessly from one stage of the construction process to another, and just minimize miscommunication and facilitate the construction, the production of projects and the construction of our cities. So that goes from integrating data analysis and taking advantage of the vast amount of data that is now available in about our cities and about the different processes that happen in our cities. So that goes from simply identifying what's an ideal site for development, and making sure that the way we develop our cities is happening in the areas where it makes sense, to developing different scenarios, design scenarios where designers can quickly generate options and compare these options based on metrics that they can evaluate, and to inform decision making, so that they don't operate blindly. But all of this needs to go hand in hand with facilitating this to everyone. So not just a few experts in the field, but everyone should have access to this technology. So a lot of the conversations that we have in developing our tool is about how we can make machine learning and AI integrate into the workflows that people traditionally have used to create design. And also thinking about what's the relevant information that we need to bring into the platform and display for people to quickly be able to quickly make decisions. And central to what we're doing is looking at how we can communicate and how we can connect different processes that are now fragmented and are happening. Different people are doing different things. How we can enhance communication through a unified platform that would allow people to transmit and communicate data more easily. So I think now I can will give a quick demo of the application, and I think we've given you guys a free trial, so you guys should be able to activate your free trial account in the email that we send you. If you guys had any issues with that, for that to for you to be able to activate the free trial, you need to first register. And once you're registered, you can just click on the link that we sent you, and you will be able to activate your free trial. So our platform is completely web-based. You would log in with your simply with your browser. I'm using Chrome right now, and you would get to this dashboard where you can store projects and create new projects. So I'll just show how to create a new project here. We have a browser that allows you to look for some city in the world. So I'll just do Manhattan. And this takes you to a map where you can search for your site of interest. once you're in the map, you can draw your site. And then what is happening now is that the platform is fetching different sets of data and collecting and making different API calls and collecting data to put together everything in one 3D environment. So we're using open data sets such as the OpenStreetMaps database. We're using other map information from Mapbox. We're using weather data from different weather stations and putting everything together in one 3D environment. So let's just wait 1 second. So now all the different data sets have been collected into this 3D environment that you can just navigate as in any other 3D software. Difference is that everything is happening on the web. You don't need to install anything. You don't need to download anything. Everything is on the web once it's loaded. And here's the site that we marked out in the map first. So you can simply start sketching some strokes and press on the play button and you would start generating design options. And there are some controls that you have over these design options. Here on the right side, you have this panel where you can select how many subplots you would like to have for your urban configuration. You can also set up your GFA. You can set up your maximum height. You can specify what the site area coverage you want. And also you can control the program mix. And once you play with these inputs, you can start generating design options that will respond to those parameters that you have sent out. And then apart from that, you can call some of our weather data to display some of the weather diagrams. And all this data that you're producing, you can also store for comparison and download to connect to other software. So if you're working with SketchUp or Rhino or Revit or any other, or we have a connection with ArchiCAD or other BIM softwares, then you can also connect the data generated here with the industry standard softwares. I think I'll leave you guys, I'll let you guys do the demo if you haven't, and you should be able to search for your any particular site of your interest and try the tool for the coming 2 weeks after you activate your free trial, after a couple hours.
Okay. Okay, thanks.
Any other questions that anyone has?
Yeah, I have another one concerning the streaming of the data. So you get the data and then you work on it. You work like in parallel on system, on the cloud, on server.
So you could have some data from a different source. Let's say we have an option to import data from, if you have a CAD file of your site plan, for example, or if you have like the specific property line of a site you're working on, and there may be other features that are given to you in CAD form, or even terrain, or even a more detailed 3D context, you can upload this data to the web. You can then use our tools to sketch out and create massing studies very quickly. And then you could bring this back to either CAD or any BIM software or Rhino or any other 3D modeling software. So the idea is that you can bring up any information that you want on the web, then also share this information with people in your organization or anyone that has access to your team account. And then at the same time, you can download this information back again and reconnect to the typical standard tools that we use for design.
Top, but probably I explain myself in a bad way. I meant the data concerning for instance, the weather. So you fetch the data from your source, and then you elaborate it. My question was more about the system, how you elaborate the information. So you do that through some cloud services, or you have your own server? How you structure the system, the workflow?
No, we're doing an API call for this weather data.
So it's just fetching. There's no elaboration. There's not calculation after you get the information in the first place.
No, for this one is just display at the moment.
Okay, clear.
Hi, Cesar. Can I ask a question?
Yeah.
Thank you for your introduction about your product. Actually, I have a question about the energy or the solarization simulation. We know that the simulation of the weather or the solar radiation is a heavy computation. So, did you use something like the cloud computation, or I mean, is it real time, or I have to wait something for the calculation if I change the architecture form?
Well, and for that reason is why we're doing, why we're looking at something similar to what Rodvik showed yesterday, using machine learning to
Mhm.
pre-train models based on some simulations, but have the estimation or have a prediction that we can work on quicker as we are generating a lot of
Yeah.
different options very quickly. We don't want to rely on a time-consuming simulation, because then that would stop the whole process of you being able to run through multiple iterations of your design very quickly. So for that reason, we're exploring the idea of using machine learning to pre-train these models.
Mhm. Okay. I think I still have another question. That is, I know that the whole process is really rely on the OpenStreetMap. Some data such as the open data. However, you can imagine that this kind of data, especially in China, is empty. If you try to search some OSM data in China, maybe you can see it's all empty. What do you think about in this kind of situation?
So for those cases, in actually many areas of the world, that's the case. So
Yeah.
for those cases, what we're doing is allowing people to also upload their own custom context data. So
Mhm.
if they have, I worked in the city I'm in right now, there's not much available data in the open sources in OpenStreetMaps, but there is from the local government some public data. It's just this hasn't been, I guess, put together in OpenStreetMaps. But in a couple of projects we've worked on, we've used this database as our source for building up the context. And actually, this data has a higher level of detail than the one that you find in OpenStreetMaps. So the plan is that if the data is not available, but you still have access to it, you are still able to upload it and customize the 3D environment that you're seeing online.
Okay. Thank you, Cesar.
Anyone else has any questions? You're welcome.
Hi, can I ask a question?
Yeah.
Yeah, sure.
If the site has a height difference, can terrain be generated?
Yeah, we can display terrain. We're also doing we're calling an API with terrain information and creating a mesh model out of this terrain. But you can also, if you have your own terrain data that is more accurate, even if this comes from a drone survey, or you have your own terrain contour lines, you could upload this onto the model as well.
Okay, thank you.
With the lab notes.
Okay. So I'll start presenting the screen. Yeah. So you all can see my screen.
Yeah.
Okay. So we'll just revise what we did yesterday. So basically, what we did yesterday is the first part of the three process step where you are generating personalized results. So the first step was to generate your own data. So we divided you in two parts. One stream was focusing on image data, the classification data, which you are drawing or sketching or even using your own Photoshop or any other softwares or Google Street Maps to generate the image data. And the other one was to generate the numerical data, CSV data in Grasshopper 3D. So I've also mentioned in the lab notes that it's actually okay to not be able to complete the process of generating your own data in Grasshopper because that thing takes a lot of time. I've also provided the data which I will be working on. That is the daylight autonomy data, and you can simply download it and follow along with me if you want, because the main aim is to make you familiar with the whole workflow, so the data generation can take time and you can follow along with the whole process later on. But if you want to learn now, you can just download that sample data. Okay, so the day two will be focusing on machine learning training, machine learning models. Okay, so this is the second step of input algorithm output, where you will be working with different machine learning algorithms. So what is machine learning models? Well, machine learning model is basically a process uh, of getting the machine to recognize or to learn some features or patterns that are present in the data. And machine learning algorithms can be basically classified into three types: supervised learning, unsupervised learning, and reinforcement learning. So for the course of this workshop, we'll be focusing on supervised learning, uh, which is classification or regression. Unsupervised learning is segmentation or say clustering or recommendation engines. And reinforcement learning is real-time learning, like the robotics or game AI, which can be done in Unity, 3D, and other softwares. Okay, so what is supervised learning? So supervised learning, we know the input as well as the output, right? So what we train the machine on is the input data and the output data as well. We give the algorithm the right answers to the input parameters, and it learns the relationship between the two, the input as well as the output. Supervised machine learning has two types, and each one of the stream will be focusing on one of the one of the types. One is regression, and the algorithm we'll be using in regression is linear regression. And another one is classification, and for that we'll be using image classification. So for regression, we'll be using Google Colabs and Python language. And for classification, we'll be using Google's web-based tool known as Teachable machines to train our model. Yeah. So
Rupik, hang on for a second. Are you going to explain a little bit about regression classification later?
yeah, I can explain it now as well. So what is linear regression? You try to fit the uh, input data with the the input parameters with the output data, and you try to find a relationship. Like if you see this GIF, it's getting to the line which is the actual representation of the relationship between input and output.
Hang on for a second. I think like I'll help over here. And also like everyone, if you think I'm over explaining or you already know this, please stop me. But let's take a simple linear equation, right? Let's go with something everyone knows. Uh, what is it, like velocity is equal to acceleration into time, right? So it is in the form y is equal to mx, where y coordinate is given by m a number and m a slope and your x coordinate. So then you get a line, and that's your relationship between x and y. Y is m times x. Now this is for something that we've already determined, but how would you like use regression for something like that? So let's say you were I don't know if it is the same you had in your high school, but in my high school, like when we were trying to find, so that's the same as finding the value of the force of gravity, right? Like you drop a ball and count how long it takes, and then eventually like you find the value of g, which is your slope. So to use regression to get something like that, what we know this relationship, but it has been like done ever since Newton discovered it, right? So 400 years, I guess. But if we didn't have that information, if we were to use regression to determine G, what we would do is we would drop the ball from the same distance or a different distance, and we would plot that here, like distance and time, distance and time, distance and time, and we would try this over and over and over again, and then you would get a scatter of these points, right? That's exactly what we did in physics class. We would get a scatter, and we would use our eyes and our brain to kind of like see what the trend is like and draw the best fit line. And sometimes it's not a straight line, sometimes it can be a curved line, in which case um, we would be told to use a broom, what do you call it, like a broomstick, like a part of a broomstick that's like very bendy, and then we would actually draw the line, and that is the relationship. See, that's the model. That's when we have that, we can predict everything else in the future according to that. So that is pretty much regression. As you can see what's happening here, as you have more data points, you get a better fit. And as you see, the red line slowly moves up and joins the green line over there. So I hope that helped. And for classification, I think it's more about distinct categorization. Rutvik, I don't have such a simple example. Like maybe Rutvik, if you have a quick, easy example, you can lead.
Thanks a lot for the explanation, Arfin.
You're welcome.
So also to add on the linear regression part, which Arfin explained, is the equation we are using is y is equal to mx plus b, is a single variable regression, and what we'll be using is a multivariate regression. And few of the examples of multivariate regression is the data set which I provided yesterday, the house price prediction, right? So you're given a couple of parameters, couple of variables, like the area of the house, or say the whether the house has parking or not, a front yard or a backyard, and these are all the input parameters, the variables. And then there is a target variable, target feature, which we will be going to predict. That was the prices, house prices in that example. And you should always keep in mind that in linear regression, you always provide the predicting, like the feature which you're going to predict should always be in the form of continuous variable. uh, like how can I explain that? uh, yeah, so the feature, say for example in this example it was price of the houses, should be continuously valued should have a continuous scale for the regression line to fit on easily.
So no buckets. What he means is no buckets. It can't
Yeah.
be like if you were to like plot a graph, like it should be a smooth line. There should be no jumps, no kinks.
Right.
For example, like velocity and time, and if the value of g is constant, it's linear, it's continuous. There's no sudden break. But there are other like we're architects, so I think like it would be easier to explain. I think if you see the strength of materials, stress versus strain, I've forgotten what to see. Here's the thing, like once you move into like technology, you forget most of the stuff that you learned in school. But like I think the stress versus strain for some materials, like you see, like after a while it stretches and then it breaks. See, that's not continuous. So you can't have that kind of variable. So I hope that helped as an analogy.
So for that, we'll be using a complete different machine learning algorithm. Maybe classification can help there because it's something like discrete groups, discrete categories of the output variable. And to explain classification in a simple manner, so what classification is, in classification, we map the input variable to discrete categorical outputs or the classes. For example, what we will be focusing on is the classes of building programs. So there are three classes which I gave you in the exemplar yesterday. Those were residential buildings, school buildings, and the commercial buildings. So what image classification will do is they know that we'll also be providing, since it is a part of supervised machine learning, we'll also be providing the label to each and every image. So they will learn from each and every pixel of that image in the rasterized image. Say that it doesn't understand anything, it just understands the pixels and the label which you provide. So say for example the label is residence, and the image you are providing is the residential buildings which has some kind of niche. So it will learn that specific feature, the uniqueness of the image which you are providing, and then it will learn certain algorithm iterations within it. That image classification is basically a complete algorithm which has different layers of uh, image recognition, you can say, whether in which it maps the image into different parts, and each part the algorithm learns certain amount of features. Like say the first part it will learn the lines and the edges or the corners, then in second part they can learn the color.
Color.
Yeah.
Yeah, exactly. So
Yeah.
so to put it simply, like the first one, regression, your output is continuous, and in classification, the output is not continuous. So you'll get buckets, you'll get like discrete categories. And I think the first and the most popular example of image classification is recognizing letters and numbers, right? I think that's the most
That's the
important.
first
So
step to
exactly,
image classification.
yeah. What is the name of the data set?
It's called the MNIST dataset.
Yeah, and if you could just share the most common tutorial for that with the users, like you can take a look at it after, and it is a good thing to know. In any case.
Yeah, so the first step whenever you learn image classification is you start with the MNIST digit recognition dataset. So there are lots of digits drawn on a black background, which makes it easier for the machine. For the basic step is black and white, so it pixels from 0 to 55, 255, and then learns using the colors provided. And the data set is quite large, and it's very good to learn that the digits are hand drawn digits, and then it recognizes and it predicts. It's actually a very nice journey to learn the image classification from digit recognition. I'll share the getting started tutorial links in the reference file as well. So let's jump into the demos now. If you have any questions in theory, you can just ask.
Notice this, as I've been teaching online too, it is hard to know what's going on. but we're obviously not our students. We're together in this. But it would be good to like hear some reactions. I don't know, like as a quick exercise, can we like, can you think of some simple examples that would work with the two types of supervised learning, that is regression and classification? Some simple everyday examples, if you can, either that you would find interesting. It doesn't have to be very complicated, and it doesn't have to be related to architecture or the workshop. Just like if you can think of certain, or it could be related to the workshop as well, that you think you could use with regression and classification, and if you could just put it in the text, it would be good for us to know as well. Just in the chat or in Discord, wherever works for you. It would be nice to have a conversation.
So I can again recap what regression is. You predict a continuous variable, and in classification you predict the classes, like discrete variables, categorical variables. Say for image recognition, image classification, you have apple, mango and orange, or cat, dog and elephant. And for regression, the example I gave is house price prediction, or say what else can be in regression, like the daylight autonomy, which is the example we'll be working on. So it's a continuous variable, like ranging from 0 to 100%. You can just think for 5 minutes and make your concepts clear. So we'll go ahead.
So a regression can also be like a forecasting of a stock market.
Right.
Right.
Yeah. Exactly.
And for a classification can be the spam filter on Gmail.
Right. Exactly.
Awesome. Yeah, that's very interesting that you say spam filter. I think they definitely use I don't know, they're Google. So but yes, the stock market. And the thing is that,
I believe they're labeling some emails with some kind of words or weird email addresses, and they put it in spam folder.
Right. Yes.
Like that.
Absolutely. So it's a simple classification whether it's spam or not spam. And it also, by the way, if you look at it, they also ask you, like, not spam, is this not spam? Did we make a mistake? And they're also learning from that.
Yeah. So actually we are tagging that emails, and they generate the data from users. So whenever they ask whether the email is spam or not, and we say okay, spam, so we are tagging that discrete variables. We are creating a class of spam, or say not spam.
So in a certain way, when you give a feedback, it's also kind of reinforced more than supervised, because you're giving feedback on if it's a spam or not. Can be considered as a reinforcement.
Yeah, it can be considered, but I'm not sure what Google's Gmail uses. But if you consider for our understanding, we can keep it in the classification for understanding. Maybe they will be using.
Here's the thing about the stock market, like, like everything breaks down to how you model the problem, right? Like ours in computational design or like a Grasshopper script, it's a design problem. Like if I asked you, like, design a chair, you could just sketch it and it's a chair, and everyone's chair is a valid chair unless somebody made a chair with like no legs. In fact, even that could be a chair. You could say it's on the floor. But then, like, when you're using like if you parameterize the chair, you would parameterize certain things only. Let's say the thickness of the seat, the length of the seat, the height of the length of the legs, the back angle, etc. So what you're doing is you're actually abstracting the problem into these parameters, and you're saying, yeah, a chair could be anything. Anything could be a chair. but like I am formulating a chair this way and I'm abstracting it into these parameters. Now with the stock market, you could say that I want to classify as should I invest or should I not invest, good or bad. That's again, that's how you formulate the problem. And then again, it's a classification problem. It's not regression anymore, right? So you see what I'm saying? Like, this is why it's good to have this conversation.
Yeah, very clear. Thanks.
Cool. Go ahead, Ritvik. Yeah, you're welcome.
Yeah. So the first demonstration is the Google Colab. Google Colab one, which in which we'll be using Python programming language for machine learning, and you can just type Google Colab on the Google search bar. Then it will take you to a screen like this. You should go to the GitHub tab and paste the link which I have provided in the lab notes. So actually, it is a Python Jupyter notebook in a GitHub repository. So by copy pasting that link, you can simply clone the notebooks which are available in GitHub as open source, and you don't need any software or any editors to be installed on your local machine. You can simply use the Google Colab. So that's the advantage of that. And when you press enter, you will see a notebook, day2ml notebook. You click on that and you're into the notebook, and you can just simply start running the code. So the first step, as I've even mentioned in the lab notes, is you need to upload the data to your Google Drive. You need to create a folder in your My Drive called as data, and then upload the CSV data which I provided, or even if you have your own, you can do that. So the first cell, just click on run anyway, because it's not Google's notebook and it's someone else, so it just asks for confirmation. And whenever you upload a data on Google Drive, so since it's not based on your local machine and it's cloud based, the notebook, we need to upload the data to your drive, and for that it asks for a confirmation. So you will get something like this, and if you go on that, you will go on another page where they will just confirm whether it's for you, and you just need to click on OK, and then at the last you will get a code, like a text code, which you need to copy and paste it in the enter your authorization code. So by this, they will get access to your drive. Like, you will get access to your drive. You can access your documents or the data, for example, now from your Google Drive, and you click on enter. Okay, so now you will get a message like mounted at content drive. So that's where I asked you to upload your data, my drive, and then upload it in data. And the next thing is loading the libraries. So for machine learning as well as data analysis, what we'll be using two libraries. One is pandas, which is useful whenever you are working with data frames or data sets. For example, the CSV data we are using. So pandas is very useful to analyze and import that data. And the next is sklearn library, which is a popular machine learning library for modeling your algorithms. And the couple of other libraries are subsets of sklearn, which is train, test, split, linear regression, and random forest regressor. So I've not spoken about random forest. I'll speak after I complete this demo. Like, it can act as a bonus of learning. First we'll learn how does linear regression work in code, and then we'll jump to random forest. So if you press on play, it will execute this code. And the next is you import your data into the Google Colab notebook with the pandas command. And if you can see the path location of my data set, it is exactly what I told you to add in the lab notes too. Like, my drive, create a document called data and then data.csv. So once you execute this code, your data is now imported in the Google Colab notebook. And to check that, you can just execute the next command, and you can explore certain things like, is it your data, and does it have the exact number of samples? Like for the exemplar data I'm using, it has 115 rows and 5 columns. Average daylight autonomy is the output variable, and there are 4 input variables: width, length, height, and window to wall ratio. Next is the command to explore your data set. So with this, you will get a detailed tabular form of exploration, like count, mean, standard deviation, minimum, maximum, and the percentages. So this is also important to check the outliers. Like I told yesterday, the outliers are the main issue whenever you are working with any data sets, and the outliers or the extremities can act as a hindrance to your machine learning model. So in this data.describe code, you can just take a look at the minimum and maximum, whether the range is correct, or you can just check the standard deviation. And you can see the standard deviation is quite well, it's around 0. For the output variable, it's a little too much. So we'll see if
You want to also like provide some more context on these terms, I guess. Like it would be helpful, I guess.
okay, yeah. So I think there are a couple of machine learning terminologies which are always used in any machine learning context or any AI context. So for that, I have even added the link to machine learning glossary, and there are a lot of terms which are often used interchangeably. So you can just go to that machine learning glossary, which is available on Google.
Actually, to be more clear, like this isn't just machine learning. This machine learning actually comes from statistics, 100%. That's
Right.
where it comes from. These are actually like statistical terms, and I think it would be so it tells you that this is what is known as describe. You see, the very fact that it says data.describe, what this is very simple descriptive statistics. And if you don't know what descriptive statistics are, to put it very simply, it gives you a generic overview of the data, like how many points there are, where the mean is, where the standard deviation. Ruthvik, can you please pull up something that has like a bell curve, and then I think that will just explain like a normal data distribution. Just for a second, like just like standard deviation bell curve, just Google it. Like,
Okay, I'll just do that. Just a second. Yep. So the normal distribution is the curve is divided exactly into 2 halves, and not a positive distribution or a negative distribution, which is inclined towards either direction. If you can see, this
yeah,
is the, yep.
yeah, and standard deviation, each of those, like you see, like those intervals, that's actually one standard deviation. Now that will depend on like what values the data has. So and then based on that, you will get a standard deviation where, let's say, like how much is like 1 sigma minus 2 sigma, how much is 1 sigma, and that's like 1 sigma is 1 standard deviation. And then that means for your data, if we're looking at the blue diagram that we have, then that means 19.1% or almost 20% of your data is like in this part, and then another and this shows a normal curve where most of it is in the center, and the further and further away you go, the lesser it is. So let's say if we were to measure like height and weight. Or I'm trying to think of something else, like, yeah, no, sorry, height given, weight given a certain height. Let's say, like, if you think of how they found BMI, body mass index, like, what should your BMI be? And then if they collected data from millions of individuals, and this is what you got. So for a certain height, let's say the height is 6 feet, or I don't know, 5 feet 10 inches. And if they found this distribution, then it means most likely for that height, the weight, whatever it is, the weight would be whatever it is at the tip. And it is very unlikely that you would find people with that height and much lesser weight. The probability of that decreases as you go on either side. So it is very rare to find someone with 5 feet 10 but with a very low weight. And it's much also the same for to find a height, to find a person with a weight which is much higher at that 5 feet 10. If this is what your distribution looks like, this means it is a normal distribution. Now, not always do you find data with normal distributions. This is a case for concern when you have when you're doing statistical analysis, and sometimes the data can be skewed. Like can you just Google skewed distribution?
I'll just show positive and negative.
Okay, yeah, so that would
deviation.
be
Yeah.
so, like, yeah, so this, sometimes you can get this, and then, like, you have to use other methods. You can't use if there's a method that you're using when the data is not skewed, you cannot use the same method for skew. Then it'll get like give you wrong results, wrong predictions. Sometimes what happens is, let's say you, in your sample, you happen to I don't know, you included a lot of rugby players and they're very well built. That will skew your data. So then you might have to remove those people if they're outliers, or you might have to use a transformation. For example, what if the variation between height and weight is not the relationship you thought it was? It wasn't, let's say it wasn't a linear relationship, but it's more of a logarithmic scale. I'm just making things up as I go. Obviously, height and weight are not related logarithmically. So then you might have to transform the data instead of, and then take the log of every number. So height and log of weight instead of height and weight. And then that would, you would want to see if you get like a normal distribution. But anyway, these are just basic statistics. You don't have to worry about these things now. But the descriptive statistics, this is what it gives you. It gives you this graph.
Yeah.
And that is not displayed in data.describe. It would be good if they had some kind of plotting tool to show that. But visually speaking, because we're visual designers, this is what it looks like. This is what it's telling you. Like what you see in this image, that is this the one that is currently in focus. Those numbers are telling us exactly this.
Yeah. So always you should always remember that whenever you need a normal distribution, which is better for machine learning model, like the normal distribution, when it's exactly distributed, it's the best for model training. And the model normal distribution is when mean, mode, and median are the same. So they are exactly in the center, and all of them are same. And if they change, then it's positive or negative, and there is a skewness in that, which can act as a bias in your training. So I guess we covered the descriptive statistics for data.describe, exploration of your data, and you can know more on that. The next step is you divide your data into two. You divide your data into two types. One is the predictor variable, and one is the predicting variable. That means input and output. So the output is always the target variable which you are focusing on. So for now we are focusing on average daylight autonomy, which we'll be predicting. So that's the target variable, and the rest all are features or the predicting variables. So y is the target variable, and if you want to if you have your own data, you can replace the average daylight autonomy by your own output variable name. You can just type in here and also change it here. So from the actual data, we remove the output variable. As I said, we are separating the input and output. The next step is we split the dataset into two types. So I'll explain more on that. One is the training dataset and one is the testing dataset. So what will the training dataset have? We generally divide it in 75 to 25% ratio, but you can change the test size here, like adding 30% as test size or say 40% as test size, because you also need to test your algorithm and check how is it performing, evaluate whether it's performing well or not when unseen on an unseen data set. And yeah, so training and test data sets. So what training data set is, you train your model on the training data set. So what the algorithm does is it maps the input variables with the output variables and finds certain relationships and recognizes some patterns and trends, and it applies those patterns and trends which it has recognized while training on the training data set to your test data set. So for testing, I'll just show you. Just provide the input and you predict the output and you can test it out. uh, in model training, the first step is you define your machine learning model. So for this, we are choosing linear regression model. There can be many, like there is support vector machines, random forest, decision trees, or KNN regression. The next step is you fit the model, which is the step in which the model is recognizing the patterns. And the next is you predict. So model dot predict on the input parameters. So in the predict function, we are not providing the output parameters, we are predicting the output parameters. We'll just provide the input parameters. So whatever patterns or trends the algorithm has learned in the training data, while mapping the input with the specified output, it will apply to the test data sets input variables and it will predict the output based on those trends and patterns.
Right. So like to slow down for a bit, these are the steps like as they look in the code, but the overall pattern is still the same. Like first, we define the model that we're saying that we're using linear regression, which means we're trying to map one variable to the other. Like I said, if we were to like find out the value of the force of gravity or the gravitational what is it, like G, like acceleration due to gravity, yeah. So so we will say that okay, we have these like values of velocity and we have these values of distance or time, whatever it is that we use. And then what is the relationship? How can we, that relationship is the G, that is the slope that we will find. Linear regression, so it's just one variable to the other, not multiple regression. And so we'll tell them that, okay, we know that there has to be like we think that it's going to be a linear regression. So let's use linear regression. And then like we give it the input data and we give it the output data, then it finds out that relationship, that which is simply like linear regression is something that we can do as humans as well. Like just like I said, just keep plotting your one value versus other. If it's acceleration versus time or speed versus distance, whatever it is that you keep plotting, keep plot, and you get a cloud of points. And if that cloud has a trend which is linear, and that when you think you can draw a line through the middle of that cloud of points, see, that is your linear regression. And once you have that, you've already fit the model. And then the next thing is to test it to see if it works. Like you get another value of speed and try to see with multiplying that by G to see whether you get the time correctly, whether it is near that line or not. That means your model is correct. You're getting the expected results. It has learned. So this is what all this is, and this is what it looks like in code. So go ahead, Rutvik.
Yeah, thanks a lot, Arvind. Then you can check the predicted results as well as you can check the real results. So the real was y test, and you can check it like what was the difference between the actual one and the predicted ones. And to get a score of your performance, like the next step is evaluating the algorithm, the model training. And for that, for regression, we use R square score. So what is an R square score? It is actually a regression score function, which is the coefficient of determination, and it maps the uh, difference between the actual test, actual results as well as the predicted results. So if you check how well our algorithm perform, it's 0.74, and this R square score can be ranged from 0 to 1. So 1 is the best one, and it can even be negative. So negative value means you need to change your data set or add more examples. It has too much of bias or it's not performing well. And 1 is the one like it's acting the best. It's exactly mapping the exactly mapping the real ones to the predicted ones. Any question till here?
Yeah, a good value for a good model, like starting from 70 or something. Like if I have a model that scores 0.6, is a good model or not?
Yeah,
Can I say this from the value, or I should be more careful about the data set and other
definitely you
information?
should be more careful about the data set too. But when you say the performance is about 0.9, so 0.9495, so these are the ones which the data is extremely clean, and it's very difficult to achieve that kind of score if you are generating your own data. If you go on with any data sets available in the open source, they are all like cleaned and super clean for machine learning. So if you run these algorithms on, like run this whole code on any of the data sets provided, you might get something around 0.99 or 0.98, so which is extremely accurate. Like you get the exact result of exact values which were in the real as the predicted ones. But now, as we are using our own generated data set, and if you take a look at the data set I'm using, it's not an integer value, it's decimal values, and it has, I think, 7 decimal values because it's a daylight autonomy, average daylight autonomy number. So it's good to have a number which is 0.7 depending on my data. And if you take a look at the number of samples as well, like I just provided 115 samples, out of which I divided 75% for training and 25 for the testing. So to improve the model performance, there are a couple of things, like you can use other machine learning models. You can check the outliers or extremities of your data set. You can add more sample points. Like 115 for any machine learning model is comparatively very less. Like you can have samples up to 500 or 1000. But since it was a simulation data, I used the Ladybug simulator to get these daylight autonomy numbers, which quite like it takes a lot of time if you have tried the grasshopper script I provided. So for that thing, I just use 115 samples. But yes, if you are getting 0.6, which is also good, but it can also be improved with other machine learning models or data set. Like you can add more samples, you can add more features to it as well. Like the features I'm providing is just width, length, height, and window to wall ratio. But the other features you can provide is the location of the house. Like I can change the city, or I can change the uh, facade direction of like the placement of the window. As of now, I just focused on the southern facade. I placed the window on the south, but I can place it on west or east, and you can just play around with it and experiment and check what is the best data set where you can get the highest accuracy.
So if I have to like make a summary, very quick summary, more feature, more data, and cleaning the data like affect a lot the score, right?
Yeah.
Clear. Thanks.
And the other point is, I can briefly explain what random forest regression does is, as I said, that changing the algorithm also matters and boosts the accuracy. So if you can see that from 0.74 it got increased to 0.81. So random forest regression is actually a ensemble method, like it's an additional, uh, how can I frame it? It's a better, you can say a better model compared to simple linear regression. Like the linear regression is very basic one. It can be upgraded to a lot of other machine learning algorithms and models. So random forest regression is, it divides the data sets into couple of data sets. Like as of now, we just have training and test data. So it also divides the training data into more number of smaller data set. It runs the regression in all the smaller data set. Then it combines the results of all the uh, all the models. Say like, okay, I'll explain. Say the training data set is divided into 5 smaller data set. The random forest randomly chooses these data sets and creates equal number of samples in each data set, and it runs the algorithm in each one, and it takes the best one out of them. Say for example, we have A, B, C, D and E as the training data sets, and the training score for each one is, say, 0.61, 0.82, 0.34 and 0.94 and say 1. So it will take 1 as the final, like the algorithm or the data set which had 1 as its R2 square. It will take that model and it will apply to the whole data set. So that's what the random forest regression does. It divides the data set, runs the model over all data set, and then takes the one which has the most or the highest accuracy or whatever evaluation metric you have chosen. So you can see a significant boost from linear regression to random forest regression. And then there are various other machine learning algorithms like neural networks or KNNs or SVMs, decision trees. So if you want, I'll give the getting started tutorial links in the reference file for a couple of other machine learning algorithms as well.
I guess typically it's just best practice to use enough sample points, so the more data you have, and especially in this case where you're generating your own data, the more you have, the better you will be able to find a correlation or a relation or a pattern in your data. And usually it's also best practice to try out different models to see which one is modeling best these relationships, and see based on the performance of each model which one you should use to model a prediction. So typically you wouldn't just go for one, you would look at different models and see which one performs best, and then you would, if you are happy or if you're comfortable with the level of accuracy that you need for a particular problem, then you can choose on a particular model.
Yeah.
I have another question concerning the random forest.
Yeah.
So basically, if you have a very good continuous data set, so the data lies more or less in the same areas, then you have a peak.
Yeah.
So you have an extreme good result. Then from your explanation, I got that the random forest is getting that result as a model, right?
Yeah.
So probably your score is going to be high, but the reality is not like fitting your data set. Can happen this kind of situation, and how, if can happen, how can you catch this tricky information? Because apparently it's a good result, but in theory it's not.
No, actually the data set is being divided randomly in all those 5 sub data sets. So I think what your question is, like, is it just like it is it acting like a bias, and like the other four data sets had a very less accuracy and this had a high accuracy, so is it wrong theoretically? No, because the when the data is distributed randomly in those five sub data sets, it also take care that it say for example you had the normal distribution, so all the five data sets will have the normal distribution,
Mm-hmm.
and out of that it will choose the best, and the divided data will not be anything like, it will not have any skewness or any outliers in them.
Clear. Thanks.
Yeah. Any other questions? So the next step is actually for tomorrow's session. So what we'll be doing tomorrow is we'll be building applications in the web-based tools, and not something like, whenever you want to create a machine learning application, you have a basic workflow, like you need to go through the APIs and cloud platforms, and then you can call the functions from the API. But for better understanding, what I thought is we'll be using a library which is present in Python, which is M2CGen library. So the next step is we'll train the algorithm on the complete data set. So above, what we did is we divided it into train and test, right? So now we want to try out new examples. So we'll train it on the complete data set. And the next step is we'll be installing that library which converts the trained model code. So the fit code, right? This code, fit, where the model finds the relationships or the patterns between the input and output data, will convert the results as well as the code of that that part of the function of model training into the required programming language. Like the application will be building is in JavaScript, so we'll convert the Python code to JavaScript code. Yeah, so you will get this function which you'll be using, so you can just save it for tomorrow. And it has converted, like what we mentioned earlier, what linear regression is. It is a function y is equal to mx plus b. So now since we are using multivariate regression, we'll have couple of more variables, so that's not y is equal to mx plus b, but y is equal to uh, nw plus mx plus b, or so on. So for that we have created a simple function which we'll be using in the JavaScript to create our applications. And you can even test out your application, sorry, the algorithm for the whole data set. Like what we did above is we divided the data set into two parts, training and the test part, and we calculated the R square, evaluated the performance, and what you can do at the last is, now you have since you have trained the machine learning model on the complete data set, so that you get a code for the JavaScript, you can simply use it in Python as well, where I say predict and I provide the input parameters, so length, width, height, window to wall ratio, and I think these are not, yeah, and I can even check that, like for those given input parameters, what am I getting as the daylight autonomy or the output parameter which you are expecting. Like this is the unseen part of the data. The machine learning model has not seen these input parameters, the combination of these input parameters, and you can test it out to check when you give a new set of input variables how the model is performing. Any questions till now? Okay, so also one example which when we were discussing I forgot to mention is the Airbnb's image classification uh, algorithm, which it is using on the images uploaded by the users. Is it uh, classifies the images uploaded by the users as bedrooms, rooms, bathrooms, kitchen, and living rooms. So this is a live use case application which Airbnb is using uh, in its process of classifying images. So I just thought of that and I thought of mentioning. Okay, so for the image classification thing, we'll be using Google's Teachable machine. The main approach of Google here was to make machine learning approachable, accessible to everyone, and uh, you can just click on Get Started, and I've provided the links in the lab notes. So we'll be using the image input data to train our model. So you can see here are two classes provided uh, as a starter in Google's Teachable machine, and you can add a third class or a fourth class or so on. You can change the name of the classes. Like for classification, we are using categorical discrete variables, right? So there are different classes. So what I'll be showing is the what my idea was to classify different building programs based on the uh, building footprints I drew on the black and white map. So maybe you have some different ideas or different classes. Like some of you might have some designers classes, or some of you might have era as your classes, or even cities. Like I saw some ideas. They wanted to classify the building footprints based on the location of the city, or the location of the building footprint in certain site or city or even country. So there you can change the classes, like you can just add Hong Kong or the name of the site. It can be even based on zoning, like residential zone or industrial zone. So for simple, I'll be just using what I have added in the lab notes, which is residential, school, and commercial. The next step is you click on the upload images, and you get an option to choose from the files which are present locally, and import images from Google Drive as well. So I asked you to put all your images of single class into one folder and create 3 folders or 4 folders depending on number of your classes. So it will take you to your, and just let me check. Yeah, so I've created the folders residence, school, and commercial buildings. So I'll go to residence, and to demonstrate I'll be using 5 images, and you can add like hundreds and even up to 1,000. Like there's no limit on Google's Teachable machine on what will be the maximum limit of images you need to upload, but that will affect your training time. Like if you upload more than say 600 or 700, the time taken to train the model will be more. Next is I upload the school images, which are located in the school folder. Again, 5 images. It's better that each class have equal number of training samples. Like for example, now I'm using 5 images for residence, 5 images for school, and 5 images for commercial building. So if you're using say 100, try to make 100, 100, 100 in each one of them. Like instead, if you use 100 images in residential buildings and just 2 images in your school buildings, or just 5 images in your school class, then the machine might get confused and the bias will be towards the residential buildings. And it is highly possible that some of your school buildings, like a lot of your school buildings which you input to check the performance of your model, that the images will be classified as the residential buildings because it has seen more of residential buildings. Think of it as a human brain. Like even you might get confused when you're given a ratio which is not equal or not balanced. Yeah, so what I did is I uploaded all the images to specific classes which I specified, and if you can see that my residential buildings have a L shape, school buildings have a niche in them, like there is a opening in certain directions, C-shaped things, C-shaped building footprints. And for the commercial, I thought that commercial buildings for me generally are long elongated buildings which are close to the streets for easier approach of public. The next step is you click on the train model button, and everything will be done completely on your on Google's cloud platform. Like there's no connection to any of your local things, and the data you share with it is not shared anywhere else, like it's in their policy as well. Yeah, so you wait for the training, and you make sure that you don't switch your tabs while the model is getting trained, because the model is completely being trained on this web browser. There's nothing else attached to it, right? So
It's your computer, so you have to keep your browser tab open.
yeah. So to preview the performance of my model, I'll just click on file here. I'll upload any image which was not in the training, like which I have not uploaded anywhere. So say I'll upload this one. So if you can see that because the images were less in amount, like only 5 were provided, it classified it as school, whereas the long and elongated buildings I had put in the class of commercial. So you know that the model has got it wrong. That's what I was saying, that uh, more number of data is better for model training. So I can try any other. Let's try this one. And always try to fool your machine, like always try to input the samples which the model has not seen, since it is a online web based tool. You don't need to worry about the uh, training process or the number of samples, whether it will be heavy or not. So you can just play around with it and improve the efficiency and accuracy of the model. And tomorrow what we'll be doing is this preview section will be converting it to a application where the user can input data, and it will be a completely customized application. You can change the way it will be presented. So for that you need to click on export model, and it has various options like TensorFlow, TensorFlow Lite. TensorFlow Lite is for mobiles, and TensorFlow JS for we'll be creating an application in JavaScript, as I said. And if you click on P5JS, you will get a complete code of your model, but it will be based on the webcam. So we need to alter this code a little so that it is upload image kind of application. So next thing is you click on upload model, and your model gets uploaded on the cloud. So you'll get a unique link. Only you can use it. Personalized data, personalized algorithm, personalized link. So make sure to copy this link and store it somewhere, because this will be useful tomorrow, as only this link will act as a bridge between the algorithm and your application. Any questions on this? So for the application side, we'll explain more about that tomorrow. And
I
till
guess
that, yeah, go ahead.
for those doing this exercise, it's worth a try with more than 5 images, not like we did here with only 5 images. for the accuracy of the model to go out to
Yeah.
be usable, train it with at least 50. I think you suggested 50, right?
Yes. So this was just a demonstration purpose, and to show the entire process in a better way, I just used 5 images, but you should have at least 50 for each class, and it's better to have more, like say 200 or 300. It's brilliant to have those many number of samples in each class, and you can just see that in the accuracy as well.
I have a question on the last step on the export. When you upload your application on your cloud, so you got the link. You have to store the link, but there is where I can see this application. It should be like inside my cloud, because checking my cloud is not there.
I guess it's not on your cloud because you have not uh, signed in for the Teachable machines. The application can be
Okay.
used by only you. The link is unique to you, and nobody else can use it. You can even check like who can use my model, and in that you can see that it's only you who can see the model. So for this application to be visible, we'll be using this link to create an application tomorrow, and then you can see the whole model or the preview application which we'll be building tomorrow.
Yes, now I see.
Yeah, any questions you can just ask, no issue.
Hi, actually, I have a quick question. And you just saw two methods to train the model, and in the final step, you just export it to a p5.java format. And maybe the next step is that you can copy this code to a website so that we can use this model in a website.
For the image classification thing?
Yeah.
Okay, so just a minute. So we'll be guiding you in tomorrow's session to create a application like footprint classification. So to view your model's performance, so you can see, you will create a customized application. Now you can see Ruthvik's app predicting building program based on footprint and context. And for that you need to upload an image, and you can see machine predicted the program as residence and confidence was 0.82%. Oh, sorry, 0.82, like 82%. So this is the next step of the training, where you translate the training process into an application, ready to use application.
Yeah, thanks.
You can see the link, which is the link of my training model, like the link generated from my training process. So this link is unique for everyone. Like when we'll be sharing the code or guiding you, you must make sure that you have the link which is of your model, which is trained on your own data, so that you will get the results and it will not affect.
Yeah, I know it. I just copy and paste the trained model link to here so that I can use it on the website or the P5. Yeah. Thank you.
Yeah. So P5 is a web-based platform where you can create applications and share them online.
Yeah. I think it's just a kind of web version of the processing.
Yeah.
Yeah, it's a kind of.
Just go ahead. Like any issues you have, in generating data and or understanding the machine learning process, or how your data will be trained? Whatever question you can just ask.
I guess for either approach, whatever you decide to do, then you can replicate the exercises that we showed today with your own data, and we will check on the results tomorrow and move on to translate this into an application.
I have a question concerning the workflow for some different kind of target. For instance, if I choose a target that I want to maximize or minimize, okay? So I generate data. So I have a bunch of data with a good result and bad result. Then from those data, I train the model, and I can predict the behavior of another, I don't know, another input following that kind of model.
Yeah.
But
So
can I say to
go ahead.
Can I say to the machine learning model, I need to maximize this or minimize this feature?
So again, that's the optimization model. Yeah, of course you can do it in machine learning as well. But when you are saying that your output should be a bad output or a good output, then that goes in the classification type of machine learning, right? And no more remains regression, where bad and good are two of the classes which you want as output.
Even if those classes are represented by numbers.
Yeah.
It doesn't have to be like cat, dog, like the previous example. It has to be like high number, low number, or you can say like a threshold. From this number below, you have a bad performance, and from this number on, you have a
that can be done. So in Python, I just showed the regression, but you can even do classification in that. So if I again go to the notebook, so here the result is a continuous numerical variable, which is from 0 to 100. So when you are saying that you want it as good or bad as the final output, you just need to change a couple of things here. Like the linear regression model will not work on classifications, but the random forest has two things, like random forest regressor and random forest classifier. So for that you need to import random forest classifier, and you just need to change this step here. Like you just need to say classifier and then click on say play, and then it will execute that code. And for classification, the R square score is not valid. So for classification, you can simply use the accuracy score. Like if you have 10 samples for testing, and say actually the 3 were good and 7 were bad, and in the predicted results also 3 were classified as good and 7 were bad, then it is 100% accuracy. So for classification, you can simply map it with number of correct, actual correct, predicted correct, and actual wrong and predicted wrong.
I believe with another method, not with the R2 score, right?
No, not with the output score. R square, yeah, R2 square. You just have the accuracy score, accuracy and the
accuracy.
Score.
Okay,
yeah,
there you go. Okay.
Yeah.
Clear.
Any other questions like regarding the whole session? If you have anything to ask on the tool or anything.
Hello. Hi. Can you hear me?
Hi. Yeah, we can hear you.
Yeah, I do have a question. I think it's a bit of a philosophical level regarding the workshop. So our workshop is named as a personalized generative design. So I want to know more about your interpretation of the word personalized. So far as I've been involved in this workshop, I understand that you somehow get the generation of the data set in a customized level and that understand it somehow a bit of a personalized manner. I want to know more about if you like define this as a personalized generative design, what different kind of aspects you like embed this concept into this process.
Let me take that. So personalized doesn't only mean from the machine learning perspective that algorithm is predicting your style. It also, I'm sorry, I'm hearing a lot of echo. Maybe somebody's mic needs to be muted. Thank you. So if you can still hear me. So it doesn't only mean the predictions. Yes, part of it is the predictions. Like, as you can see, we have a sketching tool, and hopefully we will learn more from this workshop that will help us develop a better sketching tool, because we know that not all designers work with Grasshopper. So there's definitely that aspect. On the other hand, what we see as the problem is there are many tutorials out there on machine learning, and it isn't personalized for designers at the same time. Because if you take a tutorial on how to classify letters and numbers, how to recognize letters and handwritten letters and numbers, or if you take a tutorial on how to predict the value of gravity or predict stock markets, how are you able to apply that knowledge to your personalized design process? You could have a sketch-based approach, then you convert it into 3D blocks in SketchUp, and then you use Revit, or you could be using something completely different. You could be purely doing everything in Grasshopper. So what we're trying to do is personalizing or democratizing the approach to using machine learning. And if you see the description of the workshop, we've said that we want to convert designers from being passive consumers of machine learning to passive producers of machine learning algorithms. So hopefully at the end of this workshop, you'll have enough knowledge to be able to use machine learning in a personalized way in your practice and in your approach. So I hope that answers your question.
Yeah, thank you.
You're welcome.
I can further like pursue on this topic. So today we introduced the regression model and the classification model, and understand these two all belong to the discriminative domain of the machine learning part. We haven't really touched about the generative part yet, right? But I don't know if we're gonna touch this domain as well.
So Ruthvik, maybe you can answer that. Are we gonna touch upon the generative aspect of machine learning?
No. For the course of this workshop, the main aim was to make the machine learning code as well as the algorithms accessible and available to everyone. So
Personalizable to your design approach.
yeah. So we'll not be using the generative approach, like say if you're talking about generative adversarial networks, then it's actually quite difficult for everyone to understand from a basic stage. Whenever you go on to GANs, you need to understand the basics of machine learning, and then you go through the whole process of learning regression, then classification, then unsupervised, and then you jump on to the generative aspect. But if you see now, like, people are more curious about the lucrative things the GANs are doing, but if you check the understanding of that, then it's quite low. Like, there is a code available and then people just use it, but to understand like how to make it use for designers or for architects,
To
it's
make it
very difficult.
effective, yes.
Yeah.
So we can discuss some of it definitely at the end of the workshop. And like I said, we will be also discussing interoperability, how to integrate the results of your training and your predictions with existing tools and workflows that you may have. We might have some scope to discuss GAN or the generative aspect of machine learning. Yes, and we would love to hear everyone's feedback, and also like we would love to know about like any ideas that you might have. And as we mentioned earlier in the workshop, like you don't have to follow our process. Like if you have experience, please share it with us. We will also learn from you.
Okay, yeah, sure, thank you, understood. And I saw at the beginning of today's workshop, you showed a demo of your platform, Digital Blue Form, and I understand behind that platform you might have already involved some generative algorithm, right, for generating those building blocks on the website.
Caesar, you want to take this?
Yeah, we're working with different algorithms too, and we're testing out different generative processes for designers to choose different models and launch or start triggering different AI tools or AI models that could serve them for generating designs. So one of the models we're using is based on regression. Another model we're using is based on a genetic algorithm, but we're constantly looking at different models that we can use to have designers participate and understand different ways of generating design ideas by interacting with different types of models.
Okay, yeah, I see. Thank you.
I also have a question. For the digital blue phone tool, at the back end, you mentioned that there will be a lot of different sources, databases involved. So my question is going to be, how do you ensure the interoperability between these different databases? Are you using a relational database to connect all these sources, or are you using a graph base? I mean, yes, that's my question.
Well, I don't have an answer to that. I'm not familiar with that aspect of the tool.
For our tool, we're using MongoDB for now.
Okay, it means it's a relational database, or
is MongoDB relational? It's NoSQL, I know, but is Mongo? I can just Google that for you. MongoDB, a relational database.
okay, thanks.
It's a NoSQL, yeah. So, and it's non-relational, document-oriented database management system. But these are decisions really not related to. I mean, in this workshop, we're trying to be more designer facing. That's something that an engineer, a data engineer, or a data person would decide, like what works. And yeah,
right. Yeah, which is out of curiosity. That's I know it's relevant to this course. Yes, thanks.
But yeah, thanks for the question, and no problem. Cool, terrific. So I think we can continue.
I have a quick question for Caesar. And you mentioned that you use like a generative design approach for certain topic, and for other topic you use machine learning in your platform. Can you make some example where you use one and the other?
For, let's say that the one that was displayed in the demo, we're using a genetic algorithm, a search optimization algorithm that is looking at your input parameters and trying to come close to the targets that you have set out. So essentially, the typical ways these algorithms are set out, you define some input parameters and your goals. You define your goals and your constraints, and the generator will start producing options and running through generations, getting the best options that will come close to the targets that you have, your fitness criteria or the targets that you have.
Yeah. I know how they work. So, I mean, which are the fields in where you apply it? I don't know, for calculation of GFA or other distribution or optimization of the shape. Where do you apply the one, and when do you apply machine learning? That was the question.
For the typical one that the one I showed, we're using this multi-criteria goals.
Genetic algorithm.
So so it would try to find the best trade-off.
Yeah.
For machine learning, we're using a very specific one that is looking at finding the specific relationship between, let's say, footprint area and volume. So the regression will be trying to find what will be the exact offset or exact footprint area that you need to get in order to achieve a certain amount of GFA.
Clear.
So that's set up as a linear regression.
Yeah, and also to mention that we have a lot of machine learning in the pipeline, which is going on in the research and development phase. So one of the research we are looking at is the neighborhood context. So if you look at our platform, we have a lot of 3D neighborhood, we have streets and a lot of information available. So the research we are working on is depending on the neighborhood context, like the footprints or the roads or the green spaces present in the locality, what will be the ideal footprint of the building, and then we build on it the 3D building on the footprints. So that is in pipeline actually. Quite interesting research going on.
Yeah, and here's an article by this person. He just finished his master's degree from Harvard University. He's quite famous. I think he was the first, one of the first people to burst onto the AI and architecture scene. His name is Stanis. I don't know how to pronounce his last name. Chailu, I don't know. And so this will be interesting because previously we had a question from Jillian. I'm sorry if that's how you pronounce your name, about the generative aspect. So this article has it, but unfortunately it is it's not free. And from what I know, it also has a optimization. It has an optimization side, and it has a generative side. So not only is it multi-criteria optimization, then I guess in some way there is like it determines like what the models are, and then I think it uses a GAN to generate better options. I think that's about all I understand. It's a very rough and high level overview, and I might be wrong. So, but there's the article, and if you can somehow get your hands on it, I think it will answer some of your questions.
So the research I talked about, we are using the conditional GANs as the algorithm, and as I said, we are looking at the neighborhood as the input parameters, and then generating different building footprints based on, say, it can be like different cities have different specialities. So we are looking at a couple of cities and their uniqueness to generate different building floor plans, footprints.
Okay, very interesting. I never thought about that.
Yeah, so we have a lot of things in research phase.
So you first, like, for a baseline, you look at the context, you extrapolate data from context, so you have an idea of about the footprint, and then on top of that, you can apply a generation with different goals or targets. Okay,
yeah.
Very interesting. Thanks.
So any other questions, or then we can end with the things which will be required for tomorrow. So tomorrow we'll be building the application from the from your trained models. How do I frame it? So the next step will be the output step, right? So you'll be building applications out of the machine learning models, which is trained on your data, which solves your design problems. So the visualization phase is also important, because you know what's happening, like you are generating the data, and then you are training the machine learning model. But what if you want to present it to someone, say your colleagues or professors or your clients? Then you need a prototype or application to show your machine learning, to show what you have worked on, the data generation. You cannot explain it in 3-day workshop to your client or your professor. So for that, we'll be creating an application, a ready to use application. And if you have any questions, we are available on Discord. You can just message us. Any doubts, any queries, just go ahead.
All right. Thanks, everyone.
Yeah, thank you for attending.
Yeah, thank you.
Thanks for sharing.
Thank you for the questions, and please ask us anything that you want. I mean, like we're peers. We're not